Hey everybody, Dr. A here, and in this video we're going to be going over some background information on how to compute the centroid of composite areas. Now, before we get started, I want to give a shout out to one of my best friends from college, Alan. I got to spend time with him and his family over this past weekend and catch up, and he was telling me that he watches my videos on YouTube sometimes, and so I figured I'd give him a shout out in this next video. So Alan, thanks for spending time with me and my family, and I wish you and your family the best. So let's go ahead and get started. First, let's talk about what a composite area is. So a composite area is an area composed of multiple simple shapes. Now, we often see these as C shapes, L shapes, and T shapes, but there are other composite areas that could have different shapes as well. So what do we mean by C shapes, L shapes, and T shapes? So for example, a C shape may look something like this. Right? Now this could be any orientation. You know, it could be flipped on its side and it may look more like a U shape. What about L shapes? Well, an L shape may look just like an L, but of course it could be flipped on its side or oriented a different way. Okay, and then of course T shapes or inverted T shapes. So, you know, we have the classic T shape or some other inverted orientation of this. Now, what do we mean by it's composed of multiple simple shapes? Well, all of these examples of these composite shapes are composed of multiple rectangles. So for example, let's take a look at this sideways C shape, or, you know, it's more like a U shape. We could separate each of these components of this shape into individual rectangles. We can do the same thing for the L shape and the T shape as well. So that's what we mean. We mean multiple simple shapes forming together something that is not so simple looking, okay? Now, it might not just be rectangular shapes put together. You could have triangles in the mix. You could have semicircles in the mix. You could have pretty much any simple shape that is attached to a different simple shape to make a composite shape, okay? So that's what we mean by composite areas. Now, how do we calculate the centroidal coordinates of composite areas? Well, the way we do it is we derive these formulas based on area moment equilibrium. Now, we can think of these as weighted averages. I'm not going to go into the details of that in this video. I'm just going to get right down to it. The way we calculate the x-coordinate of the centroid of a composite shape is the following. We're going to say it's the summation of x sub I times a sub I as I goes from 1 to n, all divided by the summation of a sub I, again, as I goes from 1 to n. And similarly, the y-coordinate of the centroid of a composite shape is the summation of y sub I, a sub I, as I goes from 1 to n, divided by the summation of a sub I as I goes from 1 to n. Now, at first glance, each of these formulas looks a little complicated, but it's really not, okay? Let's talk about what each of these terms mean. Now, I'm going to write that off to the side here, what each of these terms mean. N is the number of parts of the composite area. So that's literally the number of the simple shapes. So for example, if I scroll back up and I look at this C shape right here, if I separate this C shape into 3 rectangles, then N equals 3. That's the number of parts in the composite shape after you've broken your composite shape down into several simple shapes, okay? Now, what about a sub I? Let's start with that one because a sub I is showing up multiple times in this formula, in both of these formulas. A sub I is the area of part I, Okay, so when you're analyzing with these composite shapes, you have to get the area of each of its individual simpler shapes. Okay, and so the a sub I is the term that represents the areas of each individual shape. Okay, now what about these other terms here? We have x sub I and y sub I in the mix here. Okay, x sub I is the x coordinate of part I, of part I's centroid, there we go, measured from an overall origin. Okay, it's the x coordinate of each individual part's centroid measured from an overall origin. What about y sub I? Well, that's going to have a similar definition. It's the y coordinate of part I's centroid measured also from an overall origin. All right, so that defines all of these terms. So for example, we're not going to do a numerical example yet, but I'm going to give you a conceptual example. For example, if we have a composite shape made of two simple shapes, what would our formulas be for x bar and y bar? Well, what we would do is we would take these kind of bulky summation equations and we would break them down into their multiple parts. So when we have two parts, x bar is going to reduce down to the following formula. We can write x1 times a1 plus x2 times a2, all divided by a1 plus a2. And then in a similar way, y bar would be y1 times a1 plus y2 times a2, all divided by, again, a1 plus a2, okay? Now, how are these the same formulas as these? Well, again, I just expanded out the summation, okay? Now, you got to be very careful. You are adding up, let's look at these numerators. You are adding up these products, okay? So you're adding up the products of x sub I and a sub I, and that is your numerator for however many parts you have, all right? So again, this is a little demonstration of how we can expand and simplify those summation formulas when we have a composite shape made of two simple shapes, okay? So that concludes this background video. In the subsequent videos, we're gonna explore some numerical examples illustrating these. So be on the lookout for those. If you found this video helpful, please hit like and subscribe.